What's going on? Let's go ahead and start the presentation. My name is Shiari. I work in Comsol sales. Michigan is my territory. So if you have any questions about Comsol when it comes to modeling needs, can Comsol do it? Or if Comsol can do it, how can we do it? So those questions you can address to me. Any questions related to purchasing, you can always contact me. Any modeling needs, first point of contact is me. So I'm going to introduce a couple of people here. This is Hassan Munir. Hassan is going to be the main presenter today, is the expert in microfluidics. Hassan, if you want to just introduce yourself.
Okay, good afternoon, everyone. Thanks for coming to this workshop. We'll focus on microfluidics. I think it's good to see a lot of microfluidics people here. So just to give a little bit about myself, background. So my name is Hassan Munir. My education, basically, I have a PhD in chemical engineering. My research expertise was in microfluidics, magnetophoresis are the few areas which I basically expertise in. So what I've done for today's talk is basically I've divided this talk into two parts. This is the agenda for that.
Thank you, Sam. And we have Mr. Roger Pryor here.
Yeah, I'm the local certified consultant. I have a PhD in physics. This is my book. So for anybody who's interested in learning how to do Comsol, you get a copy of the book, or you can come to one of our training classes. We offer training classes in Troy, and so these are not free, okay? That's why I'm a consultant. But if you want to learn how to do it, you can do it that way. Thank you.
Thank you, Roger. So without further ado, thank you.
Thanks, Sibyl. Okay, before I start, how many of you have used Comsol or are like you're using Comsol for your microfluidics application? Okay. How many are very new to Comsol? Like have not used even the past 3.5A, 4, 4.2? No, hello? You can hear me, right? Oh, okay, great. So how many of are have used 3.5A, 4, 4.2 anytime? Very few. Okay. How many are mathematical modeler here? Oh, so all experimentalists sitting at back. Okay. So so what I have done with this workshop is I have divided into two sections. So the first is to give you an overview of Comsol 4.3a, which is our latest version. Then I'll focus on the microfluidics module, its features, capabilities. Then give you a little bit taste of microfluidics modeling, some theory. You can basically read more about that, but electroosmosis, electrophoresis, and you guys must be familiar about these subjects, magnetophoresis. And I'll go through a few example models and how we have basically used Comsol and especially the microfluidics module to cover these examples or these applications area like electroosmosis. So the first part will be more of a introductory guide to the microfluidics modeling using Comsol. The next half we will be doing a hands-on example. So that's an electroosmotic micromixer, and we'll try to make this micromixer from scratch in Comsol. So we'll use some of the concepts which we will learn in the first half and put it into implementation into the second half. So this is how we are going to do that. So before starting, if you are a mathematical modeler or if you want to model something, you should have come across these partial differential equations. And the first objective for us is to basically get information from these PDEs. They can come in one way, they can combine them together. You could basically see a heat transfer equation there, or a convection diffusion, fluid flow problem. So these are the few integral parts of anything like microfluidics modeling, or if you are dealing with some kind of a lab on a chip devices or a medical diagnostic device, you will come across mass transport, momentum transport, heat transfer, And then you have to come across these partial differential equations. And then our aim is to basically get information from these partial differential equations. And there are various techniques available where you could use basically to get information from that. So what we do in Comsol is to bring these PDEs together, either as a single way or basically in a coupled way, where two physics are together, put them in the software, and then use a technique called finite element technique basically to discretize these PDEs and get the useful information. And that useful information could be something analysis, or if you want to calibrate your experimental data, or if you want to design something, or something in the field of innovation. So then you could basically bring in different physics together and see how it affects the whole system, and whether your design is feasible or not. And those are the few things which you could do within Comsol environment using microfluidics module as well as few other modules. So this is the basic concept. So just to give you a taste of what exactly Comsol Multiphysics is, it's basically an integrated software suite where you perform all your modeling needs. So in a modeling, you need to basically design your system, you need to create a geometry, you need to mesh it, you need to choose the physics, the material properties, and all these steps are the integral part of any numerical simulation or modeling. And basically, Comsol provides that platform where you can perform these steps together. And the advantage of using a single integrated platform is that, irrespective of your physics, you just have to learn one environment. You don't really have to learn, like if you are in an electrical engineering area, you don't have to learn a different environment for that. So, and the advantage comes is basically then you can couple things together. If you are a fluid flow guy and you think that there is an electroosmosis going on, so you can bring electric fields there. So the whole environment is still the universal, it's still same. But then you perform all the physics, all the steps in the same way as you do it for different fields. So it provides an integrated software suite. And the question arises why we would like to use Comsol Multiphysics. So here are a few points which I have listed here. Just go through them in brief. So you can basically solve multiphysics problem. And if you see in nature, there is no just single physics acting at one time. They are always accompanied by many physics. For example, lightning, electric fields are there. Heating effects are there. So you have to combine them together. And if you are working in a microfluidics area, there is fluid flow, there is a heat transfer, there is a mass transfer, and you have to combine them together. So you can basically solve advanced multiphysics problem, and you can also solve advanced single physics problems if you know your second physics is not affecting your first physics. So in that case, you can still use the same environment. And the other thing is it's easy to use. So you learn the whole only one integrated suite of steps, which you can do it for electrical engineering, if you could do it for mechanical engineering. So the environment still remains the same. It's universal, but you can bring in different physics into that. And the important point is adaptability. Comsol can adapt to your needs. So if you are a new user, and if you know your PDEs, if you are solving a convection diffusion equation, you can go into Comsol, pick the PDEs there, solve it, and get the results which you want. But if you are an advanced user, if you want to do something, if you want to customize your model, so you can bring the material properties there. You can bring your experimental data into Comsol. You can type in some expressions there. You can combine it with the user interface we have already. So you can customize anything. And so there are a lot of opportunities available for an advanced user. And so it adapts to whether you are a new user or whether you are an advanced user. You could do several analysis types, do a stationary analysis, time domain, frequency domains. It depends upon what kind of problem you are working with. And of course, if your problem is big, you can break them into smaller chunks. You can use multi-code and multi-processing, high-performance computing facilities we provide, and also the clusters, which is basically supported through floating network licenses. So you could basically divide your problem into smaller chunks. So let's just visit the Comsol product suite, which is 4.3a, and let's see how it is divided, what are the different packages we have. So on the top, you can see it's Comsol Multiphysics. This is a base package. It comes with simple equations, simple PDEs, which you can use, like convection diffusion equations, fluid flow equations, very, very simple laminar flows. But then you have to enhance this functionality. You have to add on something to that, so that you could customize your model, your software environment to a particular area you are working with. So then what we have done is we have divided these physics interfaces, which are all in blue here. So these physics interfaces are defined based upon the application area. If you're working in electrical field or mechanical field, or if you're working with fluids, all the fluids physics are here. And then you have all the the reaction or the chemical fields are on the extreme right side of this blue physics interface. So for us, if we are working with microfluidics, we have to add on few more equations towards our base packet, just to enhance the capability of our base packet. So we could choose microfluidics module to that, because some of the equations which are in the microfluidics module we will not be able to find that in the Comsol base packet. And similarly, if you want to add more and more equations or more on PDEs which is relevant for your application, you can add those packages based upon if you have a heat transfer. Then we have certain multi-purpose add-on packages like optimization module if you want to do some kind of an optimization study, material library for different kinds of material, and particle tracing module is very useful especially for microfluidic communities. So they can add particle tracing and see things like, for example, you can see mixing effects. You can also see how particles behave in electric and magnetic field. And I will go through a few examples which will tell you like how you can couple them together. Then on the right, these are the few live links we have. We have live links for MATLAB. If you are more familiar with scripting, you could use those live links. Then we have live link for Excels if you want to customize based upon the Excel environment. Then we have live links for different CAD tools, so you could use those, and they can be used to basically create some kind of a geometry within Comsol environment. So especially for microfluidics community, we focus on microfluidics module. So that's the module which we'll be adding on towards our base packet, which is on the top, which is Comsol Multiphysics. But sometimes you might also need heat transfer if you are working with a bioheat transfer equation. So you might need heat transfer module, or if you are working with some other kind of two-phase phenomena within microfluidic devices, you could go with a CFD module. So those add-on packages could be added towards the microfluidics module. And then you can also add, if there are some reactions, there are more sophisticated surface reactions or homogeneous reactions, you can basically choose chemical reaction engineering. Pipe flow module is the one which basically where you are not worried about the spatial variation, but you are worried about more on the mass balance and energy balance on the endpoints of any pipe. And if you want to couple that with the microfluidics, you could do that. And then there are few other add-on packages which you could use. So basically, you can customize the software based on your needs, based on your application area. But the important thing is you should first realize what kind of PDEs you are going to work with, what kind of physics is going to affect your system. Those are the few key points before you go and add packages towards your base module or base package. So let's go quickly into microfluidics module physics interface, what we get if we have microfluidics. So first, if you know any microfluidics application will have mass transport, energy transport, momentum transport, and some of the equations we are familiar with. So chemical species transports you get, so basically for mass transport of any species, so you get transport of dilute species. Then species transport in porous media, if your microfluidic system also has some kind of porous structures, then you can basically use species transport in porous media interface. Then for the momentum transport, you could have a single phase flows, or you could have basically a multi-phase flow problem. So it depends upon what area you are working with. So you could have just a creeping flow without, or basically the Navier-Stokes equation for the fluid flow. For multi-phase flows, we can handle that using level set methods, or if you have some kind of droplets in your system, those kind of things can be handled with the level set and phase field methods, and also with the moving mesh. So these are the multi-phase features which are available within microfluidics module. Then we have more on the Brickman equation if you have more porous media, and some Darcy's laws if there are some porous. So this is what you get. And then sometimes you might also go to a region where you have a free molecular flow. In that case, where your Knudsen numbers goes higher. In that case, you need free molecular flow interface. And we do have a free molecular interface to basically capture the physics which we want to see in our system. And then you have a mathematics interface which you can, of course, use and customize your equations. So this is the microfluidics module interface, and it comes with. And you can add other modules also. You can add chemical reaction engineering if you are more familiar with surface reaction. If you think there are more reactions going on, then you can add chemical reaction engineering. So let's just briefly go towards what we get when we have a core package. We have heat transfer in fluids and solids. Laminar fluid flow is the one which you can use. Single species diffusion is what could be very, very useful for microfluidic devices. And then you get all the core facilities like moving meshes, adaptive mesh refinements, or more like post-processing and report gen. That's universal with respect of different modules. Then other capabilities which we might need for microfluidics module is chemical reaction engineering. So what extra we get is basically we get transport of concentrated species. Sometimes you cannot solve your problem assuming that it's a dilute. Sometimes there will be 2 or 3 species. Then you might have to switch to concentrated species. More on the microreactors studies, you will find that Nernst-Planck equations, reacting flows are the new interfaces which combines reaction engineering with the fluid flow together. So these are the chemical reaction engineering capabilities which could be combined with the already microfluidics module. We do have a plasma modeling. I will not be going deep into that, but this is basically used for chemical vapor deposition studies. If you are interested, I'll be happy to answer later on. Then thermal modeling capabilities. You could do anything from conduction, convection, and radiations. And if that's the need for your microfluidic system, you could also add a heat transfer module to your existing microfluidics module. It could have a more novel equations like thin resistive, conductive layers informations, and then moving domains and heat sources. Those are the few new things which you will get. Bioheating equation is what you will get in the heat transfer interface. And then you could do something like a 2-phase modeling if there is a phase change, like solid turning into liquid or like an ice melting. Those kind of studies you could do using the heat transfer module. For the fluid flow capabilities, it can range from free molecular flow to anything like supersonic flows, but that's what we will be doing in microfluidics. We'll be confining more on the laminar part or the creeping flow. Or we could go into the free molecular region where your size of the device goes very small so that the molecules basically hit the walls instead of hitting each other. So you basically then solve for free molecular flow, like more in the statistical region rather than assuming continuum in your modeling. And then you have a 2-phase flow phenomena where you could basically capture droplets, oils, and mixtures. So where you are more interested at the interface of that, then you can use discrete 2-phase flow systems. And they can be handled using level set and phase field methods of Comsol, which is available in microfluidics module. And then you can also use moving meshes also to capture your interface. We also have a homogenized 2-phase flow if you are assuming that your solid particles are mixed in some liquids and your solid is assumed to be in a continuum of certain volume. So you could use basically an Euler-Euler approximation for these kind of system where you have 2-phase flow systems. And homogenized 2-phase flow like the Euler-Euler model are basically found in the CFD model instead of microfluidics. Then you can add particles to the fluid flow towards the microfluidic channels. And so there is a particle tracing module which you can use. We have fluid structure interaction, FSI modeling. Again, if you require some kind of an FSI modeling, you could do that. We also have more on the porous structures where we have flow in a homogenized way, where we are working with Darcy's laws or Bigman equations. So this is a way how you could handle fluid flows. And then, of course, you can combine in any microfluidic channel. You are more interested sometimes to see how the mixing is going on, how the particles get captured in electric or magnetic fields. Then you can add particle tracing capabilities towards your microfluidics module. And within particle tracing module, what you find is you could add particles to the fluid flow, particles in electric field, magnetic field, acoustic field. You can also have a particle-particle interaction, as is in this example. We have a gravitational attraction between 2 particles. You could have secondary particle emission. These are the few things, formulations which you get within particle tracing module. And you could use it in a very innovative ways with the microfluidics module. You could have for flow visualization or predicting some kind of spray patterns. Those kind of studies you could do with the particle tracing combining with the microfluidics. And then if you have dielectrophoresis, more electroosmosis, those are the things you could basically look into using Comsol particle tracing module. So before I go ahead and talk more about microfluidics, let me just explain to you how the modeling works within Comsol. These are the 5 basic steps which we follow, irrespective of any application area. So the first thing is you have to draw a geometry. You have to focus on certain part of the geometry. So once you are drawing a geometry, there are a few questions which you should ask yourself. What kind of analysis is, what you want at the end, whether can you basically draw a geometry which is not 3D, can you assume something there, can you make some certain assumptions. And when you are making this geometry, you have to also think of like you are going to mesh it and you are also going to solve it. So what kind of computational resources you have so that you can solve it. also make a few other questions. So once you draw the geometry, the second thing is the physics. What physics you are going to work with? Is it just the mass transport? Is it just momentum transport? So you bring in the physics. And with the physics, you bring in your boundary conditions, your material data into the software, into the model. And once you provide that physics, you basically go and mesh, because it's a finite element technique, so you discretize these PDEs or the physics which you bring in, so you basically mesh it. And once you mesh it, you solve it, whether it is a stationary analysis, or it is a time-dependent analysis, or it's in the frequency domain. So you solve it, and finally you get the data which you can post-process it. But remember that in the physics part, you can bring in as many physics as you want. If you are a new user, we generally recommend that you go one step at a time. So you start with, for example, with just a fluid flow problem, and then you solve for the fluid flow, and then you add a mass transport there, or convection and diffusion equation. Go back and add that physics, provide the relevant boundary condition, provide the relevant material data which you want for that model, and similarly, and go ahead, mesh it, and solve the system. So this is a general process which you follow, and this is universal, irrespective of whether your application area is in electrical engineering or mechanical engineering or structural mechanics, and that's what we follow in Comsol. So let's go back into microfluidics, and I'm sure you must have come across, because you are doing research in microfluidics, and there are more expertise sitting here in microfluidics. So let's just revisit some of the concepts of microfluidics, what we are actually doing. So microfluidics, as we know, it's a fluid flow in a very microstructures or flow occurring at very smaller length scales. And when we are talking about femtoliters to microliters of volume. And this is an emerging technology where you could use it to synthesize things, to purify, to mix, to do a medical diagnostics. Those kind of things which you basically, lab-on-a-chip devices is one of the good examples where you could use microfluidics technology to build those kind of systems. So when we are talking about microfluidics, the important thing is what volume we are talking about. How small is small? So this is just a simple example. We have a cube of size 1 millimeter. Diffusion of any species is 10 to the power minus 9 meters squared. And how much time it takes to for a typical a species to basically move across that size of the cube. It's for 1 millimeter, it's 500 seconds. But if you reduce the size, it takes 0.5 milliseconds. So you can see things happens fast in microfluidics, and sometimes these things are exploited. It could be used for faster chemical reaction, for faster analysis. But there are a few pros and cons available if you reduce the size of your device, if you go into the microfluidic region. So let's revisit some of the scaling effects which you will get if you are going down to the size, if you are reducing the size of your system. So what happens if you reduce the size? So basically the volume is proportional to the L cube, or the length, the cube of the length or the size. So the cons and pros you will get is you will require less fluids, less volumes, and faster processing. This could be useful, especially in the medical area. If you have if you want to reduce the blood volume, for example, you don't want to go into the macroscopic scale if you're testing some blood samples. So in that case, your volume goes down, and that's quite useful. It could be used in the medical diagnostics area. Similarly, some other things, like some other properties like viscous forces also goes down with the length, with the size. The inertial forces also goes down, so you have more of a laminar flow or a creeping flow. When the flow is laminar, then the difficulty of mixing comes in. So most of the microfluidics devices, you want to have some kind of a mechanism to mix it. And then these phenomena like electroosmosis, electrophoresis comes handy when basically you can bring them together on board and mix the samples. Then you can also see that we have Laplace pressure, which is inversely proportional to the length or the size of your system. So if the size of the system goes down, your Laplace pressure goes up. So you could have effects like surface tension effects, which could be very, very critical in microfluidic devices. And then they can be also used in some way or the other in your system if you're doing for different kinds of application. Similarly, your permeability also goes down with the size. Diffusion time goes down, and then again you need some kind of a mechanism to mix two samples if you are working with more on the identification of any molecules, and then you have to mix them or provide some kind of an electric fields or magnetic fields to mix two species together. then you can also see the electric fields is inversely proportional to the length or the size. So the electric field effects are very important in microfluidic devices. And so like electrokinetic effects, formation of double layers, or electroosmosis and electrophoresis, they play very handy when you are working with the smaller devices, with the microfluidics devices. So, and that could be very well used to design systems. And within Comsol's microfluidics module, we have implemented those capabilities. We have implemented electroosmotic slip velocity as a wall function, so which you can use to design your system. Then we have a Knudsen number which goes down, and if you go down to a size where the molecules are not clashing to each other, but they are clashing to the walls, then the continuum approach is no longer handy. Then you need to come up with some statistical analysis, some kind of free molecular flow. In that case, we have within the microfluidics module, we have the capabilities to model free molecular flow, or in the transition region between free molecular flow and the continuum Navier-Stokes equations. So these are the few effects which you will get if you are working in the microfluidics area, theoretically if you're speaking. And then once you are in the microfluidics area, you should have some way or the other to move the fluids, because it's the movement of the fluid in a smaller volume. So there should be some kind of a mechanism how you are moving the fluids. If you talk about the macroscopic industry or macro, you have pumps, you have other ways to basically flow the fluids in them. But if you are in a microfluidic area, you should have some other ways to basically pump. You cannot make those smaller micro pumps inside those micro channels. And there are various platforms which are available within microfluidics area, where which could exploit some of the properties or scaling effects and can be helpful in basically pumping the fluid through this device for various applications. One could be like a capillary-driven flow, if there are capillary forces, pressure-driven forces. Centrifugal-driven forces is also a very innovative technique where you have a centrifugal forces. Electrokinetic-driven, where you have electric effects, where electric field goes down, you have electroosmosis. Magnetokinetic, if you have magnetic particles there. And droplet-driven, again, it's more like a surface effects or surface tension effects. So I'll just go quickly through each of these platforms and how you could use Comsol to model some of these areas. So first of all is the capillary-driven microfluidics. So capillary action occurs when basically the adhesion forces to the wall is stronger than the cohesive forces. So in that case, you will see a rise of fluids within those capillaries. And these capillary effects can be exploited in a different way. You could design something where you could have an hydrophilic and hydrophobic effects surfaces, and then you can move your liquids in a very small volume, in a small droplets. That's quite useful, especially if you're working with expensive fluids like blood, or like you are working in a medical diagnostic area. So you could use capillary, passive capillary effects in that case. You could also use electrocapillary effects. You can basically make the surface tension a function of voltage, or provide some kind of potential drop across that, and you can move the fluids. You can move the fluids, or you can move a droplet of the fluids. So in that case, the third is basically a thermal capillary effect. You have different kinds of thermal gradients within those devices. In that case, you can form the bubbles and basically help the fluid movement in those low volumes. So these are the different capillary-driven microfluidics platforms which you could use, and you can basically use some of the features of Comsol to model some of these systems. And we do have few examples there also. Then we have droplet-driven microfluidics. This is very useful because when you are talking about microfluidics, you are talking about low volumes of samples, and that's very critical. So you could basically use a drop to move two species or mix two species, and this can be done within Comsol Microfluidics module. You could basically use a level set of phase field methods to basically form the droplets and see how they mix together or how they move throughout the capillaries. So this example talks about an inkjet printer. You will see in most of the inkjet printers where you have these droplets of ink coming out from the nozzle, and then they're basically hitting the target. So this target, basically this droplet can be formulated with respect to different physics which is available within microfluidics module, like the level set and the phase field methods. This example is more of an electrowetting lens. You provide some kind of an voltage across and basically vary your surface tension. And then you can form a lens based upon that droplet, which could focus, and you can miniaturize the lenses. So again, microfluidics module could be used to model this kind of system. And then you could have something like a droplet breakup function where you have droplets moving inside the channels. And you could use the level set of phase field methods of microfluidics module. So basically, when we are talking about capillary effects, when we are talking about droplet generation, we are talking about multi-phase phenomena. You have air, or if you have a droplet, you have a liquid. You could have other species there. And then you could handle those kind of multi-phase flow within microfluidics module using either two different features. One could be like on a fixed mesh. This is more lean on the computation. And there are two methods, level set and phase field methods. I won't be going deep into that, but it's basically you're tracking the interface of the two two phases, like if you have a air domain and you have a fluid domain. So you are basically tracking that interface. And there are a set of some functions which basically helps to track that interface, and those are basically defined using level set or either phase field. They may give the interface a slightly smeared interface. You won't be able to get a very clean interface between the two, like air or liquid. But if you require something where you need a very clean interface, you don't want something smearing, then you could use a moving mesh interface in that case. So you could have very nice, but the disadvantage of using a moving mesh is you cannot handle topographical changes. If something changes, if the topography of the system changes, then you cannot really use moving mesh interface. So these are the two techniques specifically used in microfluidics module basically to handle these kind of multi-phase phenomena or multi-phase systems. Then we go to the basics thing like the pressure-driven microfluidics, where you have pumps and you basically make the fluid go through those microchannels. Navier-Stokes equation is the one which basically we follow to basically get the flow fields. And then we are talking about very low Reynolds number. It could go into the inertial effects are very negligible. So you are basically talking about Stokes equation or the creeping flow equation, which is also found within microfluidics module. Centrifugal-driven microfluidics is also a novel area where people are exploiting the centrifugal forces to move the fluids. So they can have a CD kind of structure. The CDs are moving, providing some kind of a forces, bulk forces on these fluids, and then these fluids basically follow that forces and can move within the system. And there are papers available. The cool thing about centrifugal-driven microfluidics is you don't really need any actuators, no pumps, no actuators, or no active valves. It's just the CD which is rotating, and the fluids are moving within those microchannels. Some kind of separation studies, or if you are separating blood and plasma, and those kind of things you could do with these CD-based microfluidics. And you can handle this kind of system within Comsol environment. You could get all the physics or all the PDs which you need to handle these kind of systems. Then more importantly, we have electrokinetic driven microfluidics. Basically today what I will be going is I will be focusing more on electrokinetic effects, and those are very crucial, especially for microfluidic community, and how you could use Comsol microfluidics module to handle those kind of systems. So when we are talking about electrokinetic driven microfluidics, we utilize this electric field to move fluids basically. And they are primarily used to pumps or mix fluids. The mixing is one of the issue for microfluidic system. So we basically use these electric field effects to mix them together. So there are broadly two phenomena which we are talking about. One is the electroosmosis, and the other one is electrophoresis, and also dielectrophoresis. So these are the two main phenomena which could be used in a different ways within a microfluidic system. So let's go through some of the details about what exactly happens. Suppose if you have some electrolyte composition with certain charges, if you basically provide some kind of charge to your cathodes and anodes, so what will happen is some of the charges, opposite charges, will attract towards the cathode, and then similarly for the anode. So this is what we call a Stern layer. So everything is fixed here. All the charge balances are fixed. But there is a region where you will find that there will be some net positive charge and net negative charge, and that's one of the basically the actuation mechanism comes from this layer, which is called the Debye layer, if you are working with electrokinetics and microfluidic devices. Then in the center, what you find is basically an electroneutral bulk layer where everything basically cancels each other, you can say. So you have a net positive and net negative charges here, and that can basically help in moving the fluids. So that's the driving mechanism. So once you mix the fluid movement through electric field, you could also have a convective flux, you could also have a diffusive flux, and more importantly, there is also an electromagnetic flux. So these are the three things which you will also encounter when you're working with electrokinetics phenomena. So basically what we are doing is we have a Navier-Stokes equation where we have certain force function, And then we have a Nernst-Planck equation, which also depends upon the ions which we have in the system. So these two equations are coupled together, strongly coupled together. So basically, when the force function comes from your Nernst-Planck equation, you have different kinds of charges. And within the Nernst-Planck equation, you have that convective term, which is also moving the mass or the species within that system. And sometimes we do some kind of an approximation, and there is a famous equation which is called Helmholtz-Zariski slip velocity, which is basically dependent upon the electroosmotic, basically tangential component of electric field, and there is a relation between that. So you could use that slip velocity on the walls of microfluidic channels and make the fluid move or mix. So I'll go through that in a couple of minutes. So when we are talking about electroosmotic flow, we are talking about like more of a plug flow kind of a system, where there is no smearing or there is no dispersion of anything. So this is what we call a pressure-driven flow. But if you don't have any pressure-driven flow, if you just have an electroosmotic flow, what we get a straight line, or the sample is just moving like a plug. Sometimes this is very useful because you really don't want your system to smear out in microfluidic channels. So we could employ this electroosmotic flow in our system and helps the species to move as we want based upon the electric field we provide. So some of the numbers are here. You can again go back to literature and see, but typical numbers, we are talking about 1 millimeter per second of electroosmotic velocities when we are doing. So I'll go through one example. It's an electroosmotic flow in a biochip. So the concept is we have this micro channel. This is the channel here, and we want to basically pump the fluid through this micro channel. And based upon different potential drop across these microchannels, we can pump it in a direction we want. We can either pump in this way, we call that mode A, or we could basically pump it in this way. So this is how one of the useful requirement in microfluidic community, they want to pump it in a different ways, and they can control the species in certain region. So we'll be using the electroosmotic effect, and they are basically used in lab-on-a-chip devices or medical diagnostic devices. And some of the assumptions are that we assume that there are no concentration gradients for the ions which are there, and so we can just use an Ohm's law there. And we also have a creeping flow. So instead of Navier-Stokes equation, we are assuming that there are very negligible inertial effects. So instead of Navier-Stokes equation, we are using a creeping flow or a Stokes equation for the fluid flow. So I'll be going through this example and show you how we could implement that in Comsol in microfluidics module. So the first thing is once you install the software, I hope if you have not attended the first session this morning, basically where we went through all the introductory things like how the Comsol environment look like. But this is the 4.3a version, where you can see it's basically divided into three broad categories. On the left side, you have a model builder. Then in the center, there's a setting window, and then you have the graphics window. And you can customize based upon your needs. But what we'll do is, I'll just go through this example. This is and we'll, okay. So if you have not installed the software, we do have a passcode, and we do have this USB key. You can basically download the software. It's a 4.3a version, and you can try it the expiration date is November 9. So you can basically try, and there is a microfluidics module there which you could use, and there are a few examples which I'll be going through. So I'll let you know about how you can basically come out with those examples. So you can basically install it. Here are a few USBs. If you have not done that, you can just go through it. So let's go back to our example. So we want to, the first thing we have to make is the geometry. As just remember the modeling process diagram which I showed earlier. So the first thing is to make the microfluidic channel. So on the left, you will see that there is a model builder, and then you can define that based upon, you can have a geometry first, then you can provide the material properties, then you can provide the physics, and then you mesh it, basically study that and get the results. So the first thing is the geometry. So geometry basically you can make within Comsol. If you do a right click on geometry, you can basically make those micro channels by rectangles or by using by their polygons, or you could just import that. So what I have done is I have basically imported this geometry which I have already created earlier just to save some time. So this is the geometry we are working with. This is a microfluidic channel, and So these areas, this is an outlet, so we have an outlet here, and then there are an open entries, so the fluids can come in or can go out from these regions. So all the three regions which we have here. So once I have created the geometry, the next thing is basically to provide the material property, what fluid we are going to work with. So it could be, because basically we are working with water, or you can assume something. So in this case, we have a water which is moving across this microchannel, and then some of the properties are here which are utilized with the physics. So if I go into my material section, into which is basically a water here, I get within the setting window, I get the material properties. And you will see that there are three properties which are important, because we have already put two physics there. So there is a creeping flow for the fluid flow, and then there is an electric current to get the electric field across this channel, this microchannel. So we need electric conductivity, as well as we need density and dynamic viscosity. So these are the three properties which we need to solve these two physics. And once you add the material property, they are ticked green. So this is the first checkpoint which you can make, just to make sure that you have provided all the material property to your model or not. So if it is like red cross red, that means you have not provided the relevant material property, and you need to provide, otherwise you will get an error when you are solving it. Excuse me. So once I have provided the material property, I'm working with fluid which is water. In this case, the next thing is basically I have to define the creeping flow, or the Stokes flow. So what we do is we use creeping flow interface that you can find within the microfluidics module. And if I add physics to the model, I can add physics there. And since we are working with fluid flow, we can go through the fluid flow, and then we can look for the creeping flow. So we can go into, because we are working with single phase, so we could go to the single phase flow, and then the creeping flow is here. So you just have to remember that you should know what PDs you are going to work with. So this is the PD which you are going to work with. Is it a Navier-Stokes equation, or if it is just a Stokes equation? But you can basically change that. If you don't want, if you neglect inertial terms, you get Stokes flow. If you don't neglect it, you get Navier-Stokes equation, which you have. But in this example, we are just going to follow the creeping flow. So again, next is there are three default conditions which comes with this interface, and you can see them by small d here. So by default they are there. So whatever you add later on in this model tree, they will overwrite whatever the conditions there are on the top of your tree. So this is the physics which we are solving, and we need to provide certain boundary condition to solve this PDEs. And then you will see that there are two domain conditions and one boundary. So the domain conditions are basically these blanks. The boundaries are with this purple patches, you can say. So this is boundary condition, and these two are the domain conditions. So what I do is basically I can add certain other boundary condition. In this case, since I know that this is an open boundary, these three are basically an open boundary. The fluid can come in and it can go out. So I choose open boundary, and you can find that those boundaries within the creeping flow interface. So if I do a right click on creeping flow interface, I get a bunch of different options. I can get outlet, inlet, wall. So I can look for an open boundary conditions which I can specify. And suppose if you have just an outlet conditions, as what I have done in this on the top part of this microchannel. So I have this outlet, and this outlet is selected here. So basically we do a selection in the selection box here in the settings. So this is outlet where we know that the fluid is just going to go out of this area. It's not going to come in. So we have to choose an outlet condition. So my fluid flow is defined here. The next thing is basically the electric field. I need to couple. Basically, we are doing an electroosmosis, so we have to couple that with the electric currents. We need electric currents to move the fluid flow. So I can go back and add another physics. In this case, it's an electric currents physics, and we need to provide certain type of potential drop across this microchannels. If I go back into my presentation. So you can see that this boundary is basically at 248 volts. This boundary is at 283 volts. There is a potential drop. There is a more potential drop across this boundary, where we have 79 volts at this outlet. But then I have a 213 volts here. So the potential drop is small here. So the electric field will be higher in this region. So we expect that our fluid, due to that electroosmotic effect, will basically move in this region rather than moving in this region. So we can change our potentials and we can make the fluid move in any other region. So let's go back to it. So first we have to provide the electric potential here. So I have provided that electric potential. This is 283 volts. The second one is basically at 213 volts. And then the third one is basically 79 volts. So there is a more potential drop across this line, not on the cross-sectional line. And then on the outlet here it is 248 volts. So this is how the electric field is basically is defined on this system. And then this electric field will move the fluids. So now what we have is we have two physics, but there is no coupling of the physics. There is no stitching point. How you are going to couple it? I can solve the electric current separately, and I can solve the creeping flow separately. Nothing will basically affect anything. But we need to ask for how the coupling comes into this model, how there is an electroosmotic. Thank you. So as we, if we go back to our slides, basically the coupling comes with this slip velocity. So right now, if I look at my creeping flow wall condition, which is this is the wall condition, the velocity is on that wall. It's no flow basically if you have it. But I can use that wall condition, and I can couple it with the electroosmotic velocity. So within microfluidics module, what you get is you get different kinds of boundary conditions, and one is basically the electroosmotic velocities. So I could have no slip velocity if you are just working with creeping flow, but you want that fluid basically to move based upon your electric field. So I can choose electroosmotic velocity in that case. And then I can basically choose, it will ask you from where this electric field is coming. So you need to provide that electric field. So you need to solve the electric field on this system. So the electric field, basically we are using the tangential electric field on these walls. So the electric field is basically coming from my second physics, which is EC, or the electric currents. So there will be a helping function here which will basically couple the two physics together. So you can see that this is an EC here, and EC is the second physics which I have added to this model. So my electric field is coming from there. And then we need to provide electroosmotic mobility. Some of the built-in expressions are there, but you could also have your own user-defined mobility if you have your own system, if you have a different kind of species. So now what I have done is I have coupled these two physics together using this wall condition, using this electroosmotic wall conditions. And this electroosmotic wall velocity boundary conditions comes within the microfluidics module. So if you have microfluidics module, you will get this wall condition. If you don't have it, you will not get the electroosmotic velocities. So the next thing is basically to mesh it. Once I have defined my physics, I have to mesh it because it's the finite element technique. We have to discretize these PDEs. So we have meshed it. So I've just used an extra fine mesh for that, and I have built that. So you can see that the microchannels are meshed now. And the next thing is I can just add a study to that. So I'm basically doing a steady state analysis or stationary analysis. And if I look into my setting window of this analysis, I can find that we have a creeping flow which we are solving for, we have electric currents which we are solving for, and we are solving them together. So both are like ticked green. I could have also basically deselected some of them. I could have only solved creeping flow, but in that case, your wall condition is basically dependent upon your electric currents. So I need to also solve this condition also, electric currents physics also. So I'm solving both together. And that's it. There are a few other things which you can go through the booklet if you want, but this is what we have, and we can just do compute. So right click on the study one and just compute that. So this is the velocity which we generated in this microchannels, and the maximum velocity is basically in this region. You can see that the yellow is basically 0.001 meters, 10 to the power minus 3 meters per second. So maximum velocity is in this region rather than in this region. So everything, whatever species you have in this region will basically move out through this outlet rather than going out through this outlet. I can customize few other things in this post-processing steps. I can add streamlines to that. So let's just add a streamline and see what happens there. So a streamline starting at So you can see that nothing is going up in the microchannel. I can just reduce the number of streamlines just to make it more clear. Just make it 10 streamlines. So if I look into my microchannel, most of the fluid is in this direction rather than in this direction because my potential drop was maximum in this direction. So next what I can do is I can basically, if you want to manipulate your fluid flow with the electric field, you can change the potential and you can make the fluid go in different directions. So for that, we have to provide a different kind of potential drop. So if I go back into my slides, so we need a 193 on the top and 114 on the left. So in that case, the maximum potential drop is across this area, not in this area. So you have 114 and 79. So similarly, you could basically change the potential drop and move your fluids in a way you want in your microfluidic channels. So what I can go back, and if somebody can help me with that, let's just go back. So this is on the left is 193, I guess. Then if I go back, 114 and 0, sorry. This is 0. Third one is this one. So this one is 75, it stays 75. And then the fourth one. This is 248 in the present, but I want 193. So I can change to 193. So everything still remains the same because you have now a different kind of potential drop and you will have you expect different kind of fluid flow in this. So I can go back into my study and just compute. So now you can visualize that most of your fluid is basically moving in this direction rather than going in this direction. So this way you can manipulate your fluid flow using the electroosmotic effects. Any questions so far? Yes?
Yeah, this is, your calculations are based entirely on the property of the water, right?
Yeah.
So you're assuming that whatever's in the water is going where you want it to go.
Yeah, it's just the fluid flow actually. So if you have certain species, you add another physics to it. Like if you have a species A or a species B, then you basically use the convection diffusion equations. And you couple the fluid velocity with that convection diffusion equation.
Suppose you had two fluids that you wanted to react and form a third fluid.
Okay. So in that case, you basically add a mass transfer equation. So you add convection diffusion with 3 species, and then they react to form a third species. So you could trace them. So this is just the fluid flow, how the fluid profile would look like. And that's basically utilized using the wall condition. This is the electroosmotic wall condition. So the overall idea was to introduce this boundary conditions, which is very, very handy, especially for microfluidics community if you want to. So you could mix them, or if you have other backflow, if you have a fluid pressure-driven flow as well as the electroosmotic flow, you can mix 2 things together. And something similar will be working in a hands-on, like an electroosmotic micromixer. And then we will also add mass transfer to that to see how 2 species will mix together. The next electrokinetic effect is the electrophoresis. So this is a very simple effect. Basically, if you have ions or charges, they can move within electric fields. So they can go, like the positive charge will go with the electric field, negative will oppose the electric field. So you can basically model electrophoresis also. Right now what we are modeling was electroosmosis on the surface effects, where you have liquid touching certain solids. But you could have ions in your system, and then they can migrate with the electric field. So you could also model electrophoresis, and that electrophoresis can be modeled using a very famous Nernst-Planck equation, where you have mobility term, where you have certain kinds of potential drop or electric field across your channel, which comes into this mass transfer equation. So you could have diffusion, you could have convection, but you also have electromigration, or the migration of your ions. And then you could also have some reactions if you want. So this is more of a mass balance which you're talking about. And this could be very well used for different analytical purposes, for separation or for or identifying certain types of molecules. And this is what we will do in the next example, which I'll do is basically in an isoelectric separation of proteins. This example is available within Microfluidics module. You can later on, if you want to revisit to basically see how it works and how it is done, you can go there, but I'll just go briefly over to this example. So what we are doing is we have some samples where we have different kinds of proteins with different charges. There are 6 different proteins with 6 different charges, and we are basically putting in our microchannel using this point, our injection point, where all your proteins or your mixture is coming in. The fluid flow is basically laminar fluid flow. So you have a pressure-driven flow, which basically moves these species into your channel, and they can go out from this region. But then you apply a potential drop, like you apply electric field across this channel. So you have a 0 volt on this face and 70 volts on this face. So you get an electric field across this face. So what will happen is, based upon these proteins' charges, they will deviate. They will move. If they have positive charge, they will move with the electric field. If they have negative charge, they will oppose the electric field. And there is a phenomena which is basically in isoelectric points. If we provide certain kind of a pH across pH value across this channel, at one particular pH, the charge will become 0. So what will happen is all these species will have their certain isoelectric points, and they will come together at different positions, and then they can move out of the system. So this is a very nice way of identifying different kinds of molecules, and especially useful. It's more like a chromatography applications, you can say. So in this example, there are 6 different proteins, and we can basically separate all these 6 proteins into different, and you can find the peaks of different proteins which are coming through this injection point. And we have this electric field which is moving from right to left, and then we have this sample which is coming in, but it's deviating, and then it's basically concentrating on a point, on a region which is called the isoelectric point, and isoelectric is reached using pH gradient. So we'll see how this is implemented in Comsol. So again, the similar method, as this is a universal process. You have geometry, you need to define materials, you need to define physics, and then mesh and all. So you can go through that, but this is our channel. We have this channel here, which we basically just make it with, we'll select it here, and point here, make 2 injection points. So this is the injection point we have. So my channel geometry is very, very simple. So first of all, what we are doing is we are providing certain electric potential or electric field across this channel. So what we can have is, we can have this surface at 0 volts, this at 70 volts. So we will get an electric field, and the voltage we basically provide in our parameter section, where we provide certain voltage here, 70 volts. So that's very, very simple. So you get electric field here. We assume that Ohm's law is valid in this region. The next thing is how these species will move. Basically, if I go back to my mass transfer equation, these species can move basically based upon diffusion, based upon the mobility term, based upon the convection term, and if there are some source and sink term, like if you're losing the species or if you are forming more species. So we will go one by one. So when we are using transport of dilute species, this is what we do. This is basically a mass transport equation, and this is so you should know what PDs you have to work with. So this is the transport of dilute species, and where we have fluxes which are based upon these 3 things: convection, diffusion, and electromigration. And so initially, let's do one thing. I'll start without migration. We'll just say there is no migration. We just have some species, 6 species coming in, and then they will go out with certain potential velocity. So the first thing, if I go, there are 2 terms now are basically valid: convection and diffusion, no electromigration. So for the convection, we need to provide how is the velocity field, how the fluid is flowing. If it is a pressure drop, you have solved Navier-Stokes equation. If it is just a Stokes equation, you solve for creeping flow. But in this case, we know that it's a parabolic profile, laminar flow, so we could give some analytical expression to get that parabolic flow profile within that channel. So I've already have it here, which is in the y direction, and VLAM is just an expression to give that parabolic profile. If I go back into my expressions of system here, so this is my laminar flow profile, which you can basically approximate with that expression. So I'm not solving for the fluid flow. I'm just removing the fluid flow problem by itself. But you could have added fluid flow to this system. The next thing is the diffusion, because you have convection here, U term, you have to provide diffusion also. So for all the 6 species, so we can add as many species we want. So if I go back into my transport of dilute species, there are dependent variables. I can extract them, and we are using 6 species. We could have 8 species, so there will be 8 mass transfer equations for each species. So in this case, there are 6 proteins, so we have 6, and they are numbered like 6, 1 to 6 here. So we need diffusivity for each and every protein we have here. So we need to provide that, and we just assume that it has certain diffusivity dp, which I have already defined in my system. So 5 to the power 10 to the power minus 9 meters squared per second. So this is the diffusivity we have here. Then as for other physics, we get 3 default conditions, 2 domain, 1 boundary. These are some default conditions there. But the important thing, we have to provide an inflow and an outflow boundary condition. So something is coming into this channel. So we say it's an inflow condition, and we provide certain inlet condition or the inlet concentration of these species. And the inlet condition is basically at this point, so this is the injection point here. And then outflow is basically going out of this microchannel. So everything is, whatever is coming in is going out. Yes,
when you defined your velocity profile, was that just at the boundary condition at the inlet? When you defined that it was a laminar flow?
Yeah, that's basically what we do here is, so we need to provide the velocity field both in x and y direction. So this is just in the y direction. So that's what we provide.
Just at the boundary?
Not on the boundary, on the entire domain, because that's the parabolic flow profile which we are assuming throughout this microchannel. So it will be just flowing in a laminar region. But we could have added velocity conditions here. We could have added a creeping flow to this interface. And so that's the third physics which we would have solved. Right now we are just solving 2 physics. So inflow is there. Inflow, we know the concentration of each species, which is C in, and I believe it is constant for all. Just 1,000 moles per meter cube is the species concentration, and outflow. And then finally, we basically study. So what we do is we can add as many study we want within the steps we want within the same study. So we can solve first for the electrostatics. So we are solving for electrostatics in this stationary study, but we are not solving for transport of dilute species. So once we get the electric field, we can bring them into my stationary problem of transport of dilute species, which is mass transfer problem. So next time we are solving only for mass transfer. So just the solution is basically trickling down from one set to the another. So if your mass transport is dependent upon your electric field, then all electric field solution will basically come into your mass transport equation.
What's the benefit of decoupling those into steps?
If it is one-way couple, then like if you know that the mass transfer is not going back and making changes in your electric fields, then you can just do one-way couple. So it's just a one-way traffic. You solve one and then you put it in the another one. And that is more lean on computation. Yeah. So we'll just solve that, and we have no migration term. So specifically, we don't have any effect of electric field on the mass transport. That's what we should expect. So we'll just compute that. So when you're solving, you can also look for the progress window, how it is solving. And in this case, we are using adaptive mesh refinement. So just to reduce the computational cost. So wherever the gradients are larger, the Comsol will provide more meshes in that region, and it will provide more coarser meshes in the other regions. And this is more computationally beneficial. So we could use adaptive mesh refinement in this case, because we know we have certain concentration gradients across this macro channel. And there is an algorithm built within Comsol which will sense it, and it will provide the meshes which are needed. So this is what we get. So this is the electric field maximum. It's going from right to left. So, but there is no effect of electric field on, because we don't have any migration term in our. So how the profile will look like. So this is how the profile will look like. You have certain species coming in, all the 6 species, and all the 6 species will just go out. They will not migrate across this microchannel. There is just a diffusion of these species. So this is just a mass transport. So if I look at my outlet cross-sectional values at the outlet, what I get, all my species, whatever I have provided in, basically comes out in a particular, based upon the diffusion I have in my model, in my system. So we need to couple that, because we need to do an isoelectric separation, which is based upon on the pH value also. So if I go back into my slide, so you can see here we have certain isoelectric points for these for all these 6 proteins, and they are based upon their pH values. So and we can basically move our pH gradients across this microchannel. So there is a nice way trick which is done in this example, where we provide a step function to do that. So first of all, we have to make sure that in our transport of dilute species we select migration. So now all the proteins will move based upon their mobility. So once that is done, you'll see the migration term will come in this setting window of convection, diffusion, and migration. So far so good, all diffusions are there, but then you see the migration here. And that depends upon the mobility as well as on the charge number, what kind of charges it has. So what we do is we basically provide a pH value. So we use an interpolation function for that, and say across this channel our pH values ranges from 2 to 12. So we are providing a pH gradient across this channel. And based on that pH value at particular position, so we have certain isoelectric points for all species, all 6 proteins. So the isoelectric points are defined here. So you have 6 isoelectric points. So at 3.5 pH value, this protein will have 0 charge. That means it will just stay at that position. It will not move across. Similarly, if this for the second protein, it will have at 4.7, it will have a 0 charge. So this way you can move the protein, but they will just come at have 0 charge at certain isoelectric points. So to do that, we basically introduce a step function which goes from -1 charge to +1 charge, and then we use that in when we are providing a migration charge number. So the charges can go from -1 to +1. So if it is a positive charge, it will move with the electric field, but at certain pH. So if I plot this function, so at x equals to, if I look at my interpolation function, so at x is equal to 0.5, pH is 3.5. So this is the value which we have provided with the pH gradient. So the position is 0.5. So if I go back into my migration term here, so at 3.5, the isoelectric point of first protein and this value will be equal. So that the whole value will be 0. So the charge will be 0. In that case, that protein will just confine in that region. So this is a neat way of doing this, basically the isoelectric separation, just using a step function. And we can again go back and solve this. So what will you expect now? How will be the profile look like? So again, you can check that based upon your isoelectric points. So the isoelectric points makes so for protein 1, you should expect that protein 1 should confine in a 0.5 region or in the 0.5 axis of x value. So that's what we should expect. And similarly for protein 2 and all the proteins, protein 6. So earlier the system was much more simpler. There was not large gradients. We just have a gradients in one direction. But now if I look back into my concentration profile, you will see here. So what I have done here is basically I have plotted the complete concentration of C total. So if I go back into my system here, I have defined C total as the concentration of C1, C2, C3, C4, C5, C6, 6 species, 6 proteins. And then what I am doing is I am plotting that here, C total. But if I am only looking at C1, that the protein 1, concentration of 1, so this is how the protein 1 will migrate. So all your protein is confined somewhere around 0.2. That's what information we get from isoelectric points. But there is a slight diffusion also and convection also. So based upon convection, this species goes up. Diffusion will smear the concentration, and basically electromigration will bring it all the species at one spot. Similarly, we could see it for C2. It will shift, and we can also look for C6. And we can also get the cross-sectional data, or we can plot the 1D plot at the outlet and see how the concentration looks like. And you can get that nice graphs for that, for all the 6 proteins here. So this is one of the very nice concept used to separate proteins, where you could deploy electrophoresis and to basically separate different proteins. Okay. So any questions so far? So we went into electroosmosis, we went into electrophoresis. The third one is very important phenomena, especially for microfluidics community, dielectrophoresis, and people are using it. Yes?
The models you just showed us were steady state solutions?
Yeah, they were steady state solution. So the third one is very famous phenomena is dielectrophoresis. So sometimes you could generate non-uniform electric fields, and based upon the polarizability of the particle with respect to that medium, the particle can separate. So what we have here is, if you have an electric field here, we have a lower field in this region, higher field in this region, and we have certain, there is basically particles move with more polarization. So if you have certain dipole basically formed because of the polarizability of medium as well as that particles. So you could have particles moving in the higher region, or you could have a particle moving in the lower region. So you can manipulate the medium polarizability as well as of the particles. So you have different parameters to manipulate to move the fluids or to separate it, and you could do it in a different way. So this is what we call dielectrophoresis. Some of the theories there, you could calculate the dielectrophoresis force which is acting on those particles based on this expression, and this is a complex conjugate of electric field which we apply there. The coefficient K term basically depends upon the shape of that particle. If it is a spherical, you could get something, this kind of force, a complicated equation with real part, and then you could also have an imaginary part also. The magnitude of the forces can also be computed, some of the more complex computation. In Comsol, we could use this expression, or EC norm E, to basically get those values here. So you can get that dielectrophoretic force which is working on those particles, and you can manipulate it to basically cause different separations. So there are different other parameters which you get in dielectrophoresis. You can manipulate medium, you can manipulate particles, you can manipulate, of course, the geometry of the system. So in that way, you could basically cause the separation or mixing. So I'll just go through this example. I won't be going into the Comsol. This is more a sophisticated model. So we have an electric field here. This is just a simple block where we are just want to see dielectrophoresis phenomena. The red electrodes are at 10 volts in this case, and the blue ones are at 0 volts. So there is a potential drop there. Electric field is created in that region, and then the particles will move based upon different kinds of forces which are acting on the particles. So it could have a drag force because you could have certain fluid there. If the fluid is flowing, there will be more drag force on that. There will be a gravitational force, or because of the mass of that particle, and there could be a dielectrophoresis force, and many other forces if you think. So they basically,
in that case, we don't have a real particle. We see only the presence of
the particle. That's correct.
What if we want to see the deformation of that particle? Can we do
that? Yeah, you could do that. That could be like a fluid structure interaction. So like your particle deforming, and then it also influences the fluid flow across it, and then the fluid forces the particle to deform in a certain way. So that's more like a fluid structure interaction problem that could be done on a moving mesh interface. Yes, Comsol can handle that.
Can Comsol also handle the fluid breaking into two pieces?
You mean like it's a two-phase phenomena, more like a
So you'd have to add the two-phase.
Two-phase, like you could use a level set of phase field methods where you have different kinds of surface tension or Laplace pressure there. So in this example, this is just a simple example. We have drag force, we have gravitational force, and then the dielectrophoretic force. And the dielectrophoretic force basically comes from your buffer or the medium which is there. It has certain conductivity and relative permittivity. Then we have two different types of particles there. We could have a positive DEP or a negative DEP based upon the conductivity and relative permittivity of the particles. So in this example, we can calculate the forces on that based upon this expression. If you want to get more information, you can look into literature, more on the papers on dielectrophoresis. You will find this is very common equation which for dielectrophoric forces. Then we have a complex permittivity of medium, complex permittivity of particles. These are the two things which you could manipulate, which you could change, and then you can calculate the Clausius-Mossetti factor. This is also basically related to dielectrophoresis, and based upon that, you could either have a positive DEP, negative DEP, how positive and how much negative. So everything will depend upon your medium and the particles there. So in this example, we choose two particles, which one showed a positive DEP, the other one showed a negative DEP. And then the other forces like the gravitational forces and the drag forces. If you have a fluid flow flowing into that channel, then you could also have a substantial drag force on those particles. So this was simulated in Comsol using Microfluidics module. We calculated basically, we use particle tracing in this case. So particle tracing was combined with the electric fields here. So we have particles, the red ones basically showed a positive CM factor, and the blue ones show the negative. So we can see that we can separate the two particles. So the positive ones goes towards the high field region, the negative goes into the low field region, and this way you could basically separate them together. And you could use this, you can use this model, you can develop this model based upon the particle tracing module and the electric field. So you really don't need the convection and diffusion or the mass transport equation for that. The next phenomena I'll just go through is a magnetokinetic driven microfluidics. So now you have talked about electrokinetics, you have talked about capillary pressure driven. The magnetokinetic driven microfluidics is also a novel area where microfluidic devices have been developed. You basically put certain types of magnetism inside the channels. You could have magnetic nanoparticles combining with proteins or with certain cells, and you give certain magnetic entity to these particles, and you can separate it from non-magnetic entities. So the way you can deal within Comsol is basically it can be classified into two broad things. You could either use the drift diffusion analysis based upon the diameter of your particles which you are working with. So if FDP is greater than KT, the temperature and Boltzmann constant, if it is yes, you can use the Newton's law of motion, basically where you have basically other forces, the magnetic forces, fluidic forces, and gravitational forces. But if it is, you can also, if the particle size is very small, you could basically use a drift diffusion analysis. So more of a continuum approach to find a solution for how the particles move. So you have certain concentration of the particles instead of each particle. And in this one, in one of the examples, basically we assume the Newton's law of motion. We assume that FDP is greater than the force on the particle multiplied with the diameter of the particle is greater than KT. And therefore we use this with particle tracing and magnetic fields. So this is a simple magnetic microfluidic bioseparation. You could combine that. So we could have a magnetic field. We can define it in a magnetostatic equation, or it could be defined in AC/DC physics. You could just have a magnetic field across a domain, and we can then calculate the magnetic force on each particles. And one of the, if you go into the literature, one of the famous forces are given by Suzuki et al. It depends upon the magnetic field gradients, the volume of the particle, and certain other parameters. So you could get magnetic force on the particles, and then you could also have a fluid flow, because you could have a fluid flowing, carrying these particles into the region of magnetic field. So again, you can use Navier-Stokes equation with an inlet and outlet. And this fluid basically causes the drag forces on these particles. So you can calculate the drag forces, and finally you can see how these particles deviate or move with respect to drag forces. So it's a balance of drag forces with the magnetic forces. So if the magnetic force is greater than a drag force, the particles will move towards the high magnetic field area. If it is low, it will go with the flow or go with the fluid. Yes?
How much wall conditions are these going to influence the overall design of this thing?
if it is a creeping flow, it depends upon the drag force. You can calculate the drag force on the particles. And if it is too low, that means the magnetic force is the real force which is acting on the particles. So this is an example where we have a fluid flow carrying two different types of particles. One is magnetic, the other one is non-magnetic. This is the magnet here, simple neodymium magnet, supplying a magnetic field in this region. And then you get forces on these particles. So for the non-magnetic particle, there is a fluid flow which is coming from this region and this region, which confines all the particles to go from on the top outlet rather than going in this outlet. So if the particle is non-magnetic, it will just follow the fluid flow, the water flow, and then just goes out. But if it is magnet, there will be a kind of deviation from its path, because the magnetic force will try to pull these particles in this fluid region. And then when it comes in this region, it will just go out from this channel. So in this way, you can basically separate a magnetic particle from non-magnetic particle. And these magnetic particles can be basically used as a carrier particle with certain proteins, you can have a chemistry where you can combine magnetic particles with certain proteins or with certain DNAs or certain cells like E. coli cells, and you can basically separate them together. So this is what I have so far. Let's just go through this 6 points to get started with. If you are new with microfluidics, there are different ways, different innovative things you could do with microfluidics module combined with particle tracing and AC/DC and Comsol. So these are the few basic 6 steps which I would encourage you to go through. This workshop will give you an overall idea what you could do with microfluidics. I haven't touched the two-phase phenomena, but you could also go through two-phase things. There are a few examples which you can go through. Work through the quick start booklet. Basically, we'll be doing one hands-on module and then hands-on model. So just go through that. If you are unable to complete that model here, you can go back home and try that model and try to run that model exactly as it is in the model library. Go through webinars and tutorials. We keep on posting latest tutorials and webinars there. Just go to the website. Then the most important thing is the model library examples. We keep on updating more and more microfluidics models also. So you can look into that model library examples. So I'll show you in quite a while just how you can browse through those examples. You can also go on the website to basically get those models, and there are also user papers there which might be very relevant for your own application or your own research area. So the important thing is create your access account, go to the Comsol website, create your access account. This will help you to basically download the models. There is a user interface, there is an exchange community there, there is a blog also, so you can go through the blog, browse through the blog and see what is new within Comsol and community. Then we have a specification chart which is useful, like if you are new to Comsol and if you want to know what modules should I have, or whether I should just have a microfluidics module, or should I also have a like CFD module or a structural mechanics module. So what in specification chart, what you will see here, you can find all the physics here, and on the top you will find different modules. So if you are looking into microfluidics, so I can tick on the microfluidics here, and what are the physics I get is basically on the left side, so you can see them. So if I'm working with two-phase flow phenomena, it is found within microfluidics module, and similarly other modules carry different other physics. The contact and web info, you can write general inquiries. If you have some technical support, you can write to support@comsol.com. You can use this contact and web info page to basically contact us. If you have certain other applications, if you want to talk more about how you could solve those things within Comsol environment, please feel free to talk to technical support. You can write to technical support. I'll be here throughout the hands-on, and I can answer some of the questions there, focusing on microfluidic systems, or if you have your own applications.